All right, I also want to talk about the horizontal line test. So we have the vertical line test, and now we also have a horizontal line test. So a function f has an inverse that is a function if there is no horizontal line that intersects, the graph of the function at more than one point. So it's basically the same test as the vertical line test, but we do it horizontally. And if you can find a horizontal line that hits more than once, then that function does not have an inverse. And I kind of tried to summarize that a little bit here. So the vertical line test checks to see if the graph is a function, and the horizontal line test check to see if the function has an inverse. If both vertical and horizontal line tests are passed, we say that we have a one-to-one function. And a one-to-one function is in which no two different order pairs have the same second or first component. So what you see there is that the x values and the y values do not repeat when looking at a set of points. So remember, for functions, if the x value repeated and that same x value went to two different y values, like we saw in the last example here, then that was not a function. But we didn't worry about if the y value repeated. So now we're looking at both. If something is a one-to-one function, then what's happening is your x values and your y values are not repeating. So every set of x values is unique, and all the sets of y values are unique there as well. So let's do an example here with the horizontal line test. So if you have a graph, you're going to use the horizontal line test. Now, they're telling us that all these graphs represent functions. So it represents a function because they've already passed the vertical line test. So horizontal line test is about inverses. And then just is it a function is the vertical line test. So if you look at all these graphs and you try to do the vertical line test, they all pass. So these are all graphs of functions. Now we're checking, does it also have an inverse? So if I look at this one here and I try to draw horizontal lines through, I see it only hits once. So because we only hit once, this does have an inverse. So this passes the horizontal line test. Something like this right here, see how it hits twice? So this fails the horizontal line test. So it does not have a function. I have an inverse, excuse me. This one here also fails, right? If I draw right here, I hit 1, 2, 3 times. I just need to hit twice. So this one also fails that horizontal line test. So there is no inverse function. And this one here is a little harder to see, but it actually passes. So this hits once, etc. So it's around right here. Maybe it looks like it would fail, but it doesn't. It's still slightly increasing, so you're not kind of bumping back up there. So this one passes the horizontal line test. So we do have an inverse function. Okay. So you have two different tests here. The vertical line test just tests, is it a function? And then the horizontal line test checks, does it have an inverse? Okay, so sometimes they get a little bit mixed up. Vertical line test is it a function? And then the horizontal line test to see if it has an inverse. Okay, if you pass both, so these ones here that pass both are called one-to-one functions. So that means that there are no repeats on the x-axis and no repeats on the y-axis. So all those points are unique. You're not getting repeated values there. And those are always our nicest cases. They're the easiest to usually deal with. So if you pass both, you are a one-to-one function. So I mentioned this a little bit in the first video, but I want to come back, like I said I would, to more about inverses and their graphs and how they relate to those original functions. So there is a really nice relationship between a graph of a function and its inverse. And again, these would both be one-to-one because if you have an inverse, you would have passed both vertical and horizontal line tests. So if AB is a point on the first function, then BA is a point on the inverse function. So for instance, so for f of x, let's say the point was 2, 3, then on the inverse function, you would have the point 3, 2. So you get that swapping or that opposite of those values. And what happens is you actually have a reflection about the line y equals x. So here's just one example. Not every graph has to look like this, but here's that line y equals x. And then here is the original function. Here is the inverse function. So what happens is the point here and the point here are exact opposites. The points flip. And you have this reflection right along that line. So if you were to fold your paper, along that line diagonally, you should get that those graphs are matching up. So that's what you see with functions and their inverses. It's really actually really interesting, I think, that not only do they cancel each other as equations and they're opposites that way, they're also opposites graphically. So they do actually form reflections like this diagonal reflection from each other. So let's use the graph below to draw the graph of its inverse function. And then I also want to find the domain and range of each case. So one thing to note here, so this is our original function. It does pass the vertical line test, so it is a function. And it passes the horizontal line test. So if you check this mentally, you pass both tests. So we have a function and it's going to have an inverse. So I do know that I can find the inverse. So for my function here, I'm just gonna make a little table. I'm gonna note my points. So I have the point -3, -2, -1, 0, and then 4, 2. So for your inverse, let's use a different color. You're going to get that swapping. So here it's going to be -2, -3, 0, -1, and 2, 4. And then you're going to follow the same shape. So everything here are line segments. So I'm going to copy that shape. So I have -2, -3. Let's see, 1, 2, 1, 2, 3. 0, -1. And then I have 2, 1, 2, 3, 4. And again, I'm going to copy the shape. So I have a line segment here. And then it was a line segment here. So this is your inverse function in pink. All I did was take those points, I swapped the values, and then I just copied the shape, right? So both of these were line segments, so I just connected them with line segments. And notice you have that diagonal reflection, right? If you're looking at this line, like right here, you can see that would be the line y equals x. You can see that you have that nice reflection diagonally. So those are your inverse functions. I also want to find the domain and range. So I'm going to start with my blue graph here, okay? So my domain in this case, if I look at the original function, my x values go from -3 all the way to 4, and that's it. And the endpoints are included. So my domain is from -3 to 4. And my range are my y values. So I go down to -2, and then my highest y value is +2. Now for my inverse, let's check out our domain. So our domain, these are, remember, your x values. So I go from x is -2 up to x is +2. And then for my range here, those are my y values. Let's see, my pink graph goes down to -3 and it goes up to 4. So notice what happened. The domain from here became the range from here, and the range from the first one became the domain from the second one. And that is not a coincidence. That always happens for inverse functions. They swap. And that's because we're swapping the x and the y. So you're getting the opposites. So it's really nice because actually if you have information about one piece, then you already know the other side. So if I know my domain and range here, I don't have to do any extra work. I know my domain and range here. I'm just going to switch them. Or a lot of times what we end up doing, just as a little side note, is we'll often find the domain here and the domain here, and then use that to give us the ranges instead. So there's different ways that you can use this information. But if you have one, just know that you have the opposite for the inverse. So if I have the domain for F, I already know the range for the inverse. It's the same exact value. All right, I'm gonna do one more example here. Let me zoom out a little bit on this one. All right, so we're gonna do a few things. We're gonna find the inverse, and we're also going to graph on the same plane. Okay. So I want you to notice this does have an x square with it. And I know we saw before that x squared did not work well, right? It wasn't a function when we tried to find the inverse, but we have a restriction here. So this is a little bit different. So maybe we should graph it first. So I'm going to do x and f of x, which is x squared minus 1. And notice my restriction here. My restriction on our function is that x has to be 0 or greater. So when I plug in values here, I can't plug in any negatives. I can only plug in 0 to positives. So maybe I'll plug in 0, 1, 2, and 3. So if I plug in 0, 0 squared minus 1 is -1. If I plug in 1, I get 1 squared, which is 1, minus 1 is 0. If I plug in 2, 2 squared is 4, minus 1 is 3. And if I plug in 3, 3 squared is going to be 9, minus 1 is 8. So again, if I'm doing those in my head, but if you need to write out the work, you can go ahead and write that out, right? So for example, if I plug in 3, then I have f of 3 is 3 squared minus 1, which is 9 minus 1, or 8. So I'm just plugging in those values, and I'm just choosing a few here. All right, so let's set up our grid. All right, so I'm actually going to graph my original function first. So let's see, I have 0, -1, 1, 0, 2, 3, and then my 3, 8 is going to be off the grid a bit, so I'm just going to leave it for now. So it'll be 3, 1, 2, 3, 4, 5, 6, 7, 8. So it's like up here. So I'm just going to go ahead and just graph this the best I can. So it's going to look like that. Now notice that I don't have the entire function. Because there's a restriction here, I only have the right side of that function, right? I'm only using 0 or positive values. So if I graph this, I see it as a function. It passes the vertical line test. But now because I have the restriction, it also passes the horizontal line test now. So this is different because I have that restriction. I'm not looking at the full U shape of the graph. I'm only looking at the right side. So I do pass that horizontal line test now. So there is going to be an inverse. And actually, even before I find the equation, I actually could find the graph. So if I want to find the inverse, because I know it exists, because it passes the horizontal line test, all I'm going to do is swap these values. So this becomes -1, 0, 0, 1, 3, 2, and then it would be 8, 3. So if I graph that, I'm going to zoom out just a little bit more here. So let's see, -1, 0, -1, 0, 0, 1, 3, 2. So 1, 2, 3, 1, 2. And then 8, 3, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3. It's going to be like kind of like over here. And my graph would look like this. And you can see that you do have that nice kind of diagonal reflection here, right? You don't have to draw the other line, but you know, that y equals x line is basically running right through like this. Okay. So you have that nice reflection. I'm able to find that graph even without knowing the inverse function yet as an equation. I just found my original graph and I swapped those points. I saw my original graph pass the horizontal line test, so I knew I could do it. I swapped my points and I'm able to get the graph right away. Now let's go ahead and find the equation to go with it. All right, so I'm just going to rewrite my original function and then I'm going to move down so we can see some work. All right, so now let's actually find the equation here. So remember, your first step is to replace the f of x with y. And then I'm also going to now swap. So remember, those x's and those y's are going to go ahead and swap. And I also can swap here too. So I end up with x equals y squared minus 1, and y has to be greater than or equal to 0. So I swap out the restriction as well. And now I'm going to go ahead and I'm going to solve for y. So I'm going to add 1 to both sides. And I'm going to take my square root. Don't forget, it's an even root, so it's plus or minus. And now I'm just going to rewrite it up here so we can see it a little bit clearer. All right, so now you may be saying to yourself, okay, it's the same thing we did last time. You told me there was a function here, but it's plus or minus. This is not a function, right? If it's plus or minus, but we have a restriction. So remember here, we have that restriction here. Now it's y is greater than or equal to 0 once I swapped out my x and my y. So if y has to be greater than or equal to 0, this negative 1 goes away. I can't have y equals a negative answer. My y has to be 0 or positive because of my restriction. So that is going to make that negative piece go away. So actually, it's only the positive root of x plus 1. So now this is a function. So the inverse function is the square root of x plus 1. And you can see here, notice we're taking a root and we're adding, and then our original graph was a square, and subtracting. So again, you have those opposite operations here as well. But I like this one because I wanted to show you with a restriction. So not every restriction is going to work, but usually we restrict our functions in order to make them work so we can find inverses. So here we took a function that normally does not have an inverse, because when you solve it, you would get that plus or minus idea. But because we put a restriction on it, a specific restriction that made it a horizontal, so that it made it pass the horizontal line test, then we were able to now create an inverse that is also a function. So that's something that's really common as well, where we have a lot of these applications that do involve squares or fourths and things like that. So if we apply a restriction, then we can kind of narrow down that original function so that it becomes one-to-one and we can find its inverse.